Okay, so we'll just get started with a roll call. Again, these meetings are voluntary for sub-basin committee members. We do a roll call just to note in our record if there is a quorum present, but we won't be taking any action. So this is again just for our record. Well, I guess first I will call the meeting to order now at 1:03 and then begin with a roll call. Here. Okay. Horacio Amezquita.
Here.
Brian Barrientos. Christopher Bunn. Adnan Chaban. Carolyn Chapin-Hodges.
Here.
Ross Clark. Tom Francione.
Here.
Brenda Granillo. Robin Lee.
Here.
Colby Pereira.
Here.
John Bramers. Jerry Lohr.
Here.
Steve McIntyre.
Here.
Christina Nunes.
So they heard me.
Alan Panziera. Ron Panziera. Brad Rice. Jason Smith.
Here.
Tom Adcock. Elahe Esfahanian. Brett Malone. Beverly Bean. Patrick Breen.
Here.
Janet Brennan. I got you, Janet. Margaret Ann Copernall.
Here.
Sarah Hardgrave.
Here.
Ron Stefani.
Here.
Bob Jakes. Andrea Bailey.
Here.
Mark Bloom.
Here.
Jeffrey Crank. Grant Kramers.
Here.
Bill Light. Roger Matoiso.
Here.
Jason. Okay. I'll also try to go back through for people who just joined and make sure I've captured your attendance as well. So now going on to public comments. So these, let's see, I guess I should read this. If you are joining by phone, please press *9 to queue for comments. Written comments can also be submitted. But does anybody have any public comments at this time? Okay. Let's see here. Margaret, you still have your hand up. Is that from earlier?
Yes.
Okay. All right, I'm gonna lower your hand. And Nancy Isaacson.
Hi, thank you, Nancy Isaacson. I just wanted to, it's probably for the next item, but I did want to ask for when a copy of the slide presentation or the power presentation would be made available and posted to your website. So thank you.
My pleasure. After the workshop today, we will post it. We have that workshop page that we're building on where we've been providing both a recording as well as the PDF. And Norm?
Thank you. Can you hear me?
Yes.
Yeah, I'm just wondering with all that's going on locally here with the fire suppression activities, whether it would be worthwhile to start collecting data on how much water was used to suppress the fires for future reference.
Yeah, that's an excellent comment. And yeah, and they're probably getting it from so many different places too. I don't know if they're tracking that themselves.
You know,
But-
every single gallon that they are tracking, every single gallon, it will come from all different places, but every time they know exactly how much retardant and exactly how many gallons of water have been put on the fire.
And do you know if they track the source? You don't know.
I honestly, I think they probably do. I will ask specifically. I've got a good friend at CAL FIRE who's been giving me all this stuff, so I will ask that question and get back to you.
Okay, any other comments? Okay. So moving on to our scheduled items, we have Derek Williams here with Montgomery and Associates, who's our groundwater sustainability plan consultant, and he's going to be talking about our watershed, basically how it works, overview of surface water and groundwater infrastructure in the basin. It's going to cover some basic geohydrology concepts, and then also go into more depth into groundwater surface water interactions in order to understand some of our unique challenges here and some of our water budget conversations coming up. So with that, I will pass the baton to Derek.
Great, thank you very much, Emily. So yeah, we were asked to present this presentation when we were developing workshops that people would be interested in. We were asked to give a presentation on the watershed. And so we've put this together as a high-level overview of the valley, where the water comes from, where it goes to. What I'd like people to get out of this is some context for the project, the projects that are already in place in the valley, how they work, and the projects that we will be talking about over the next month. In fact, starting next week, we are having subcommittee meetings, sub-basin committee meetings, where we will be talking about what projects should we be analyzing in more depth. And so what I'm hoping people get out of this presentation is enough understanding that they have a context of why projects are there, what the constraints are, and what might work and what might not work. I will try and stop at a couple places during this presentation for questions. Please hold on to them until I get to a certain place, unless you have a real burning question, then you can either raise your hand or interrupt if you haven't figured out the raise hand issue yet, which most people, myself included, have a hard time with. So the goals of this workshop are to explain effectively how the Salinas Basin works hydrologically, and floating the surface water and the groundwater. And talk to the stakeholders about the water budgets, how they're set up, what's important and what's not important. We are not going to compare the geographic extensive institutional boundaries. The institutional side of how the Salinas Valley works is a whole nother subject. This is going to be very much the physical side of it. So I'll talk a little about the overview of the valley. I'll start with a little bit about how the surface water works, and then go to the groundwater, and then talk about a couple special challenges. Seawater intrusion notably. It's going to be important that everybody knows how seawater intrusion works if you want to know how the basin works there. So,
Derek,
yes.
excuse me, just wanted to, Norm, you have your hand up. Do you have any technical question or?
No, I was just asking if you could ask everyone to mute. There's one phone that seems to be coming through with some background noise and interrupting Derek's transmission.
I just got them. I just muted them.
Thank you.
Thank you, Norm. Okay, so let's start with just a picture of where we are. This is the Salinas Valley watershed that I'm showing on the map. The watershed is the area that you see outlined in pink. This is the area that provides surface water to the Salinas River there. A couple things you will note about it. At the north end, part of the Langley subbasin, part of the Monterey and Seaside subbasins are not part of the Salinas River watershed there. The streams that come out, there are no streams really in the sand dunes over here. That's what makes them, that's because they're sand dunes. And the streams over in the Langley area do not actually feed directly into the Salinas River there. So they are actually officially not in the watershed. Down here in the southern portion in San Luis Obispo County, this does actually officially eventually feed into the Salinas River. I think when USGS put together their map, they considered this the Estrella River watershed, but it ends up in the Salinas River anyway. So the pink area, when I talk about the watershed, that's the area that I'm talking about. The grayish area and the green area, so all this internal outline is the groundwater basin that we talk about here. So all the way out to this green area, that's the groundwater basin. That is mainly completely within the watershed, but not always, as I mentioned here at the north end there. Both surface water and groundwater are used as a water source in the watershed, and I'll get to that in a minute. The point I want to make in this is that ultimately all the water we use in this watershed comes from rainfall. The valley doesn't import water from outside the watershed, although water does come across the county boundary through the Salinas River. It's not imported really from outside the watershed. It's still inside the watershed. The other point I want to make, because all water ultimately comes from rainfall, is the issue about pumping deeper and deeper. It only has temporary benefits. If we pump groundwater from a deeper aquifer, these aquifers are effectively reservoirs, and we have to replenish that reservoir. And the only place we're going to replenish that reservoir is somehow capture and use rainfall to replenish it. So pumping deeper has some benefits. They're often temporary benefits. I do want to say it basically expands the size of our reservoir, so it is advantageous to use all the reservoir space you have. If we pump from deeper aquifers, we're basically saying we're expanding the size of our reservoir, and that's a good thing. However, don't forget it is a reservoir that we have to replenish with rainfall somehow, and so we still have to manage the surface water to get out to replenish those deeper aquifers if we're going to start using them. That's a key factor to think about when we're talking about projects here. Rainfall varies by season and by year, and I'm going to talk about that a little bit, about the variability of it. But that's sort of one of the take-home messages, is that we need to manage our surface water in order to manage our groundwater. As I mentioned, rainfall is variable across the watershed by season and by year. And so this is the across the watershed story. These are isohyetals. And that means these are lines of equal average rainfall. And up here at the top of the Sierra de Salinas, where my cursor is right now, that's the highest rainfall area. That's what you might not be able to read this, but that's about 70 inches of rainfall annual average in this area. It's centered north of Cone Mountain here, and that's important because the mountain kind of stops some of the storms from getting farther south, so you get a lot of rainfall north of there and a little less rainfall south of there. There's a big difference. The Cone Mountain is a big orographic impact on rainfall here. It's also the area where all the major streams start from. You also notice on this that the amount of rainfall on the east side of the valley as you go up into the Gavilan Range is much, much less than the amount of rainfall on the west side of the valley. It gets up to 70 inches here, and it's getting up to about 15 to 17 inches on these lines. So most of the rainfall and most of the water we have for management is going to be coming from the west side of the valley. When we talk about projects in a week or two, that's going to be important. As I said, water rainfall varies spatially and also by season and by year. Here's just a couple graphs. I will tell you quickly what they mean. So at the Salinas Airport, there are two graphs, the top left and bottom left. And these two graphs show the normal water year in red, what the normal rainfall water year looks like, and the 2015 water year, which was very, very dry, one extremely wet month, and then very, 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 very dry. And the cumulative, you can see this blue line is below the red line. It says the amount of total water we got in 2015 was far below normal. Okay, whereas in 2019, it was slightly above normal, and we had a much more spread out. The blue bars here are much more evenly spread out. We had much more evenly spread out rainfall. King City, kind of the same story. We had, in 2015, we had one month of, it was in December, of high rainfall and fairly low everywhere else. And we ended up with relatively low rainfall for the year. King City in 2019, we had well spread out rainfall, a couple of very high months in January and February, and we ended up with much, much more rainfall than on the blue line here than the average year down here. So that's the description of how rainfall is variable both in space and in time. And when it's in time, it's both in time by month and in time by year. Those are all the problems we have to work with. Now, the point of water management, and this is not an official definition, but we want to smooth out all those variabilities. So we want to provide reliability by decreasing the seasonal variability, the interannual variability, and the spatial differences in water availability. That's pretty much the core concept of what we're trying to do with water management. So that's the problem, this variability, and our water management is the solution. Now, when we try to smooth out all these differences, we have to think about all the users also, the environmental, municipal, domestic, agricultural, and I even put recreational on here, even though we don't think about them much. The reservoirs are a recreational water use, and they do have some need for the water there. So we try to address all these issues when we talk about water management, but they do have competing interests. So that's the very fundamental purpose of what we're going to be talking about with how the basin operates today and how we want it to operate in the future. As I mentioned, sorry, I thought there was a question. I mentioned earlier that there is both surface water and groundwater use in the valley, and this gives a graphic of how it's distributed. The big blue in this pie chart is the agricultural use, basically. It's about 80% of the all the water use in the valley is agricultural. And that's not a surprise to anybody. When I look at the other parts, municipal groundwater pumping constitutes about 2%. So that's 82% of all the water used in the valley comes from groundwater. About 1% of the water comes from the Clark Colony diversion. I highlighted Clark Colony simply because it is the largest surface water diversion in the valley. Not because it's more important or less than any, but it is the largest diversion by about a factor of 4 in the valley, and it still only constitutes 1% of all the water used in the valley. The CSIP diversion is another 1% of the water used in the valley. About 13% of the water used in the valley comes from other surface water diversions. And about 3% comes from water provided by the Salinas Valley Reclamation Plant from Monterey One Water. So that's kind of the distribution of where we get our water from. I do note at the bottom of this that about 2% of the water is reported both as groundwater and as surface water diversion. And so I did not take it out of any of these pie slices, but it gives you an idea of how big a pie slice it would be. About this light blue slice, that's about the slice that you could take from one or other of these slices because it's reported as both there. So that's where the water comes from there. And that's how the water is used in the valley there. So I did remember I said all the water comes from rainfall, but clearly most of the water, the vast majority, is used as groundwater. It's the primary water source for users. So the issue we have is we need to get the water from where it is, the rainfall, to where people want it, which is the groundwater. And that's the point of the projects. And that's the point of the projects we're going to be talking about in the GSPs. These projects are designed to help groundwater users without impacting or minimally impacting environmental or other surface water users. That's the balance we're trying to gain here. So let's talk about the first part. And after this part, the surface water part, I'll take questions then. Let me take questions now. Is there anything on the background that people want to ask?
Derek, this is Steve.
Yes.
On that last chart, that pie chart, it was hard to see some of the colors on the right-hand side. So Clark Colony is 13% or 1%?
Clark Colony, boy, those did come out almost the same on this now, didn't they? They looked different when I first made this. Clark Colony is 1%.
And the 13% is?
Other surface water diversions. If we total up all the surface water diversions that are reported in 2017 to the State Water Resources Control Board, it turned out to be about 13% of all the water used. Now, like I say, some of that is also reported as groundwater pumping.
Right, got it. Thank you.
Sure.
Okay, and I do see a few questions from attendees, but I'll just take this moment to note that we do have a quorum in the Langley, Monterey, Upper Valley, and Four Bay Subbasin committees. So thank you for your attendance, and we'll note that for the record. And now I saw James Tynan's hands first, and then Nancy Isaacson. So James, I'm unmuting you. You should be able to talk.
Hello, can you hear me?
Yes.
Yes.
Yeah, I was just wondering, are we going to be this evaluation, will it cover the deep aquifer around Marina, between Marina and Castroville?
These GSPs cover this. As far as how the basin works, those deep aquifers work the same way that all the other aquifers work, except they are deeper. And as I mentioned, it is often more difficult to get recharge to them. And because of that, that is my caution about using them extensively until we have a methodology or know how much recharge we can get to them, because they are a reservoir like any other reservoir. It's good to use reservoirs, but you always have to refill reservoirs. So I'm only going to talk about the deep aquifer in the context of how all the aquifers in the 18400 and the Monterey subbasin work.
Thank you, Derek. Thank you.
Okay, and Nancy Isaacson, I believe you're unmuted. Go ahead, please.
Thank you. Thanks, Derek. I wonder, your note at the bottom says 2% reported as groundwater pumping and surface water diversion. So, and then you have 13% other diversions, which you said are, I think, reported as surface water and or groundwater. So is the 2% of the 13%, or is it 2% of the total?
It's 2%. Yeah, thank you, Nancy. I'll clarify that. It's 2% of the total. Let me talk a little about that 2%. That 2% are diversions that when we looked at what was reported to the State Water Resources Control Board and what was reported to Monterey County Water Resource Agency as groundwater pumping, we felt confident that the values reported were identical or close to identical, and the location was identical or close to identical. So we could say these were reported to both places. So one thing that happens, that 2% might be something of an undercount if we made a decision that they're not in quite an identical place or something, we might have undercounted it. The other point that I want to make here is, yes, it is 2% of this pie and it is not shown. Since they were reported both as surface water and groundwater, it actually, they show up. They show up both as part of the 13% and part of the 80% of agricultural pumping. So this pie would be slightly smaller if we actually took that 2% out, but we did not want to make an assessment of which pie slice we should take it out of. We just wanted to make it a footnote saying this pie is slightly smaller and some of these slices are slightly smaller. We're just not sure which pie slice to reduce right now. Did that help, Nancy?
Well, kind of, I guess, because then if I understand you right, and I thank you for that, but 2%, then that means 13% or if it's 2% from the 13, it still leaves 11% that you're saying is actual surface water diversion. And I still believe that's high. We've had this discussion many times that I think many of the growers who report do duplicate. And I'm just very surprised that it would be that high of actual surface diversion. So thank you.
Yeah, and thank you for that, Nancy. And that does get back to my first point that we are only, that 2% is only diversions that we're very confident we could say this is a diversion and pumping. And so we might be underreporting that 2%. I think there's quite a bit of work that has to be done along those lines, but I think that is work for the future right now. And that will be, there is no doubt that in the future, the question of are you pumping groundwater or are you diverting surface water is going to be a major question. It wasn't for this presentation, but it will be as we go forward with projects and implementation. Thank you. Yeah. Any
Okay,
other
now we
questions? Yeah.
Robin Lee.
Derek, what is Clark Colony divert from? I'm not that familiar with them. So what are they diverting?
Clark Colony's diversion is on the Arroyo Seco.
Okay, thank you.
Yes.
That's, just checking. Thank you.
And as I point out, I only included it here because it is the largest surface water diversion in the entire valley and still only makes up 1% of the total water use. The largest diversion isn't that big. Yeah. Okay.
Okay, I don't see any other hands.
So I'm going to talk about the surface water section now, which I call getting water into the groundwater. Basically, where's the water coming from? Getting back to the watershed question, there are 3 major watersheds in Monterey County. I say in Monterey County because the watershed goes on into San Luis Obispo County, and there's the Estrella River up there and the headwaters of the Salinas River. But we're only going to talk about what we're managing with these GSPs, which are these 3 major watersheds. There are a lot of other smaller watersheds, but these are the 3 that drive groundwater management. They're the Nacimiento River watershed, which is this teal colored watershed at the south end, the San Antonio River watershed, which is more the reddish color in the middle, and the Arroyo Seco watershed, which is the greenish colored watershed in the middle of the picture there. 2 of these are dammed, as almost everybody knows, the Nacimiento and the San Antonio rivers are dammed, giving us the 2 reservoirs, and the Arroyo Seco is not dammed. They are all roughly similar in size. However, as I mentioned, that orographic influence of Cone Mountain changes how much water goes down each of these watersheds based on their size. And basically, you end up with relatively more water in the Arroyo Seco for its size than you do in the San Antonio watershed for its size. And I'll talk about that in the next slide. So this is the inflow. This is flow in 2017. And what I'm showing here for the 2 reservoirs, Nacimiento Reservoir on the left and San Antonio Reservoir in the middle, this is the inflow to the reservoirs. These aren't releases. So this is some measurement of how much water was available in the watershed. And you see the Nacimiento Reservoir gets much more inflow than San Antonio does. And if you listen to any of Water Resource Agency's presentations, when they talk about the Interlake Tunnel, they say, in general, Nacimiento Reservoir fills about 3 times faster than the San Antonio Reservoir does. And it turns out in 2017, the ratio of inflow is almost exactly 3 to 1. It was actually 3.01 to 1 or something like that. So my point here is you can actually trust the Water Resource Agency when they say that. The right-hand side, the Arroyo Seco is not dammed, so I don't have any graphs on what the inflow to any reservoir is on the Arroyo Seco. What I'm showing instead is the flow at 2 gauges on the Arroyo Seco. The blue bar goes up to the gauge near Release Creek. And so that is the gauge very close to where the Arroyo Seco enters the Salinas River. So this dark blue bar is an estimate of how much water came from the Arroyo Seco watershed and entered the Salinas River. And as you can see, it's not as much as water as we get from Nacimiento, but it is more water than we get from the San Antonio Reservoir there. So it's a significant contributor to the Salinas River there. The light blue stippled area above it is the flow at what's called the Arroyo Seco near Soledad gauge. This is upstream of the Release Creek gauge. So this is kind of a measurement of how much water is coming out of the mountains and into the productive part of the Arroyo Seco cone, the very sandy part. And as you see, it is more water that comes out of the mountain than actually gets to the Salinas River, which emphasizes a point that I'm going to make in a minute. There is significant amounts of recharge from the Arroyo Seco River into the Arroyo Seco cone before we ever get to the Salinas River there. This actually represents a significant amount of water. So of the three watersheds, when you think about them, when you think about how much water is coming from these three watersheds and how much we have to manage, here is a quick view. Now, I should emphasize, this is a one-year snapshot. We chose 2017 for these analyses because 2017 was a relatively wet year. Water management should have worked generally the way we want it to work in 2017. We weren't a lot stressed by lack of water, and so we weren't able to manage water the way we wanted to. So this was a good snapshot in time. It doesn't mean it's exactly what you're going to see every year or even average, but it should give you a visual of how the surface water is working and where our water is actually coming from. Well, as I mentioned on the Arroyo Seco, a lot of that water from these surface water systems recharges the groundwater. So on the undammed Arroyo Seco River, it turns out if that stippled area, if I look at it if you look at sort of what the median recharge is on the Arroyo Seco cone, on days when flow gets all the way to the Salinas River, not just any old day, but when the Arroyo Seco is flowing strong enough that flow gets all the way to the Salinas River, you're getting about 265 acre feet per day of recharge in the Arroyo Seco cone. So that's pretty significant. That river puts a lot of recharge into the Arroyo Seco cone and still gets to the Salinas River at a pretty high rate, at a rate that still adds more water than, it shows more water for the year than is flowing into San Antonio Reservoir. So that's quite a bit of recharge comes from the Arroyo Seco. Salinas River, we get recharge from the winter flows, and I haven't quantified that because the winter flows are, the basins are generally quite full, but also you get conservation releases from Nacimiento and San Antonio. And these are kind of the summer releases from Nacimiento and San Antonio reservoirs. And these are the releases that are intentionally to get water to other water users downstream, among other things there. When we look at those releases, we're getting quite a bit of recharge. We're getting about 880 acre feet per day between Bradley and Soledad, and another 600 acre feet per day between Soledad and Spreckles, most of that probably before Gonzales there. So there's quite a bit of summer recharge coming from these conservation releases. These are releases that are intentionally done to help this out by Water Resource Agency. As a map of it, a little complicated map, these are the winter flows and these are the summer flows. The winter flows, for example, these are average daily flows for 2017. Winter, I believe we chose November to March, and summer, I should have written this down, was something like May through September or something like that. These are basically, though, the summer flows are basically the conservation flows. So you can see in the winter, we have a reservoir release. We pick up a lot of water coming out of San Luis Obispo County, and that's why when you get to Bradley, you have so much more water. And then you get some percolation. You have less water when you get to Soledad, This is the Arroyo Seco coming in at a fairly high rate. So you have even more water near Spreckles and about the same amount of water. There's very little infiltration between Spreckles and the lagoon below the SRDF. In the summer, and this is what most people talk about, the combined, these are in cubic feet per second, the combined releases are about 776, almost the same near Bradley. You don't really lose much water by the time you get to Bradley, but you lose a lot. This is what I was talking about. There's a lot of infiltration by the time you get to Soledad. Nothing's coming in from the Arroyo Seco in summer. And then there's a lot of infiltration before you get to Spreckles, and largely, I believe, before you get to Gonzales there, or around Gonzales, that area. And then not much infiltration by the time you get to the lagoon. So what these two reservoirs are doing, they're balancing the spatial and temporal variations in precipitation. We're holding back water and we're able to release it when we need it there. And basically we're taking water, we're taking water from the high rainfall areas in the Sierra de Salinas, and we're being able to redistribute it to some degree, at least to the center of the valley. Not so effectively to the east side, but at least to the center of the valley.
Derek, you have a couple questions. Is now a good time or do you want to wait?
That would be fine. I can take them. Yeah.
Okay, Steve McIntyre, please go ahead.
Thanks, Emily. Derek, on the summer flows, I think it's important to point out that while you have a 0 there for the Arroyo Seco, especially in 2017, the river is flowing underneath what we call the Green Bridge on Elm Avenue at a fairly decent rate through maybe the middle of August or the 1st of August, and is providing some recharge into that cone that you talked about. So I think it would be important to estimate or quantify that.
Thank you for that, Steve. Yeah, and you make a good point. I am breaking up this conversation into surface water and groundwater. And I think one of the take-home messages from this presentation is we have to manage them together, and they do work together. And as Steve points out, recharge, and it's significant in the Arroyo Seco cone. If it's not pumped out while it's in the Arroyo Seco cone, it is a benefit to anybody downstream there. There is a lot of water that is, that's actually probably a benefit just by keeping groundwater elevations high for everybody. There is a benefit all around for that. So thank you for that, Steve.
And Robin Lee?
Derek, I was wondering if you have any idea how the smaller watersheds that ring the valley, because there's a lot of alluvial fans around the valley. You see the wiggles in the boundary of the groundwater basin. There's a lot of alluvial fans. Is there any estimate of how much water is coming down from the smaller watersheds?
Yeah, Robin, good question. There's only a couple gauges. I think there are 2 gauges on the smaller watersheds on the east side. And we have estimated what that might mean for the other small watersheds. We will have those are in the 180-400 GSP. There is a map and a table that estimates kind of their relative flows for these small watersheds along the east side. I don't have that with me, but I can certainly provide that to you.
So do you have the values for the west side as well? I mean, is there any way to estimate? So I was looking at the numbers below Arroyo Seco. You got 4,000 acre feet difference. Is there a way to kind of estimate how much they could be contributing? And then of course, a lot of these are infiltrating. They may not even get to the river, but they're infiltrating.
Yeah, we have not done that, Robin. If we need to, we certainly can do that. We would do it the same way we've done for the east side. Robin, can you mute yourself? Is that you, Robin? Somebody?
Yeah, there's background. Thank you.
Thank you. And we certainly can do that. It's done the same way we do for the east side. Hydrologists look at these things and they look at sort of the size of the watershed and the amount of rainfall, and they basically correlate what might be in one stream compared to a stream that we know about that's already gauged We've done it for the east side, and we can certainly do it for the west side if we need to, or if it would help our groundwater management, we certainly could. But we have not done it yet.
Yeah, well, that's significant. I mean, there's a lot of, I'm sure there's a lot of water coming down there that we just don't quantify. But
Okay.
thank you.
Okay, now we have a question from an attendee, Justine Massey.
Hi, thank you. I just wanted to follow up with a comment that you made earlier, Derek, about how this is a very wet year that you're using the numbers for to look at this. And I understood your explanation for wanting to see sort of where the strongest flows come from when everything's working well. I wanted to know, like, how big is the discrepancy between what comes via surface water during this wet year and then like the more common trends that we've been experiencing?
It's a good question. There is a significant difference if you look at the hydrographs of some of the rivers when you look at peak flows. I don't know about total flows. I know in peak flows, you can get some significant differences for wet years. After this presentation, I might have a slide at the end. I will look to see if I can show you a slide that's buried in the back that shows peak flows and shows the difference between various years. But I don't have the numbers for kind of totals anywhere. It can be a significant difference is all I can say, yeah.
Okay, thank you.
And by the way, I am reminded that our flow numbers on this, the winter flows is December to March, and the summer flows that we're showing are June to September. So that's, I misspoke, and that's what we're talking about here. Okay. Okay. So another type of recharge, since we're talking about recharge, you should be aware that from a hydrologist's viewpoint, in-lieu recharge is the same thing as active recharge. This is going to come up again when we talk about projects starting next week. But CSIP, which is, as everybody knows, is the program to provide water, various sources of water to growers at the north end of the valley. And by providing water in lieu of them pumping groundwater, from a groundwater hydrologist viewpoint, that is functionally the same as having a recharge program. So this will come up when we talk about projects a lot. These are some numbers from August of 2017 and February 2017. You can see that in August during the summer, we're delivering considerably more water than in February because August is part of the irrigation system in general. There's relatively little irrigation in February. But the point that I want to make is when we talk about recharge and total recharge, in lieu recharge is going to count as recharge, and it may come up in other situations besides CSIP, especially things. In lieu counts as recharge. You could almost consider fallowing as recharge, basically some way to prevent the impacts of pumping. But particularly throughout the state, this has become a hot topic, making sure that people recognize in lieu recharge is a recharge program, providing surface water, recycled water, or desalinated water. Those are all, as surface water, those are all considered recharge programs. I think we've gotten most of the questions. Are there any others now, Emily? If not, I'll go on to the next section.
Don't see any hands.
Good. So that is the quick overview of water above ground. And what we want to do with it is get it into the ground so people can use it. And what's happening now, which is the reservoir operations and CSIP, those are our basic recharge programs now. Now the question is what happens once it's in the ground? So how do people use the groundwater? As you all know, the groundwater basin, this is a picture of it in Monterey County, covers about 530,000 acres. There are 7 subbasins in Monterey County, one being adjudicated, the Seaside subbasin in this area up here, up in the upper left corner there. And I only bring that up because it is legally in a different position than the other subbasins are. The key here is that the subbasins are all connected to some degree. So similar to the river, which goes from one subbasin to another, groundwater flows from one subbasin to another to some degree. Sometimes it flows easily, sometimes very poorly. And I'll talk about that. I'm going to talk about each one and sort of what the subbasins are like, but they are all to some degree interconnected. I want to point out that the subbasins are not defined. The reason water flows from one subbasin to another is because they are not defined on any real physical structure that stops groundwater flow. And this will be more readable to you possibly when you get the actual presentation. But for example, the outline of the Langley subarea is simply the topographic change from the upland to the flats. So there's nothing about that topographic change that says groundwater can't flow across it. The Monterey subbasin is divided by the Release Fault there from the 180-foot aquifer. There is really some question as to whether that fault is a barrier to water flow. I don't believe it's much of a barrier. The eastern limit of the western limit of the east side aquifer is probably the closest we have in the valley to some barrier to groundwater flow. It's not really a barrier, but at least there's a geologic change there that says groundwater doesn't flow easily from the 180, 400-foot aquifer into the east side aquifer. The southern end of the 180 and the northern end of the forebay is simply the limit of confining conditions, or at least where it was estimated, the limit of confining conditions, but that doesn't mean water doesn't flow easily across this boundary. Similar between the upper valley and the forebay. This was actually defined oddly on the influence from the Arroyo Seco, that they said in the upper valley, you don't see that much influence from the Arroyo Seco River. And so therefore we're going to call that its own subbasin. But that means nothing about how much water can flow between these subbasins. So I'm bringing this up to say we have all these subbasins. Don't think of them as divided from each other. They are named for various reasons. They are identified for various reasons. Very few of those reasons are any physical barrier to flow. I want to make sure everybody understands some basics about aquifers and aquitards before I go too far into it. Aquifers, as almost everybody knows, is something that has large pores between sand grains. So it allows water to flow very rapidly, and we think of that as a high hydraulic conductivity. Think of going down to the beach and pouring water on beach sand. It disappears immediately. That is an aquifer. Beach dune sands make great aquifers if they happen to have a lot of water in them. So they have a high hydraulic conductivity. Gravels, sands do. Aquitards, when I say that, they are small pore spaces in silts and clays. Think of that as a low hydraulic conductivity. Think if someone's throwing pottery and they pour water on their clay, it doesn't soak into the clay, it spatters all over the place as they spin their potter's wheel. That is because the clay, which is an aquitard, doesn't let water pass through it fairly easily. As long as everybody understands that. The other thing you need to remember is the difference between unconfined and confined aquifers. Unconfined aquifers, such as this, are not capped by a clay. So when you drill into an unconfined aquifer, when you first find groundwater, your well, the water level in your well will be at this blue line here. An unconfined aquifer is like a bathtub full of water and sand. That's the way you think of it. A confined aquifer down here has a clay cap on it. And what the effect of that clay cap is it pressurizes often this confined aquifer. So confined aquifers are less like a bathtub and more like a pipe filled with sand and water. You can pressurize it, but it has a limit on how much water you can stuff into it. And the point there is that then when you drill into one of these confined aquifers, even though the top of the confined aquifer might be fairly deep, the water can come up fairly high in your well. So that's what confined aquifers are. You can get water to come up fairly high, but remember, most of the storage space, remember it's hard to push a lot of water into a confined aquifer. Most of the storage space happens in an unconfined aquifer. So that's the difference between them, and it makes a difference in the different subbasins that we're working with, when you're working with an unconfined aquifer and what that means for how you manage it, and when you're working with a confined aquifer and what that means for how you manage it. Because to get water into a confined aquifer, you either have to find the outcrop, which is the recharge area up in the hills, or you've got to inject water into it. Whereas an unconfined aquifer, you can recharge it simply by percolating water through the soil, and it will get to the unconfined aquifer. I'm going to start by talking about the 3 subbasins along the valley's south to north axis. I'm going to sort of walk through each of the subbasins now to tell you what makes them unique, what makes them the same, and how they're connected with each other and how they operate. I want to start with these 3 along the axis because they are all connected. They are all very similar in some ways and slightly different in some ways there. But they tell kind of a nice linear story south to north. The story kind of falls apart when you get off to the sides of the valley. So I'm going to start with the easy approach here. So these 3 subbasins are the Upper Valley, the Forebay, and the 18400 subbasins. They're all defined by fluvial deposits from the ancient Salinas River. When we say fluvial, that means deposits from old rivers. These are river deposits there. And river deposits have a tendency to be linear and well connected with each other. Yeah, they have a tendency to be, long sand strings, long clay layers, things like that. I do point out the Forebay subbasin has a significant coarse alluvial deposits. That's the Arroyo Seco cone. So although in general, these basins are defined by the Salinas River deposits, the Arroyo Seco cone adds its own deposits to the Forebay and makes that somewhat different. Like I say, so they're all defined by pretty much the same depositional system, but the aquifers become more confined going south to north. And that's important based on what I just talked about, how you recharge aquifers and what it means for where you can store water and how you can get water into the ground. So you'll see a progression south to north of effectively more and more confined. And because of that confinement, there's less recharge from the Salinas River in the north because of those geologic constraints. So going south to north, you would start with the Upper Valley subbasin. For each of these, I'm going to show a cross section. And if you are not familiar with a cross section, this is basically a slice through the earth and looking at the earth on side. These cross sections come from the 2015 State of the Basin report. And what we're seeing is the gray areas are clays, generally clayey or silty or not good producing, and the whiter areas are the sandier areas. So in the Upper Valley, you see big areas of sandy. Actually, you're seeing more clay than I would have expected here, but you see big, large sandy areas. And because of this, there's no extensive clay that goes the entire valley, and we think of the Upper Valley as a single unconfined aquifer. It is just one big bathtub of clay and sand. Now, locally, it will look different, but as a basin as a whole, we think of it as a single aquifer. It gets significant recharge from the Salinas River. However, I should point out that there are now areas, the way that the DWR has defined the boundaries of the Upper Valley, there are now large areas away from the river that don't see the benefit of recharge from the Salinas River. So that's an issue we're going to have to start dealing with as we go forward. For each subbasin, I'm going to show a hydrograph, a typical groundwater level hydrograph, and this is one for the Upper Valley. You can see, except for the recent drought, which is in this area right here, that's the recent drought, groundwater levels are held fairly constant. And that is because of this large amount of recharge they get from the Salinas River. The very sandy soils, the amount of recharge they get from this there. It's the first basin in line to get recharge. Basically, the Salinas River keeps this basin at a very high groundwater level. When you move to the Forebay, couple things. First of all, this is the Arroyo Seco cone I was talking about. This is the outline that I am using now for the outline of the Arroyo Seco cone, and it's where there are some coarse sediments, particularly to the west. The sediments in the Arroyo Seco cone get much more like the Salinas River deposits when you get over to the east, over here. But this is the Arroyo Seco cone, and that's a geologic feature that makes this area somewhat unique here. When we look at the cross-section of the forebay aquifer, we see that the clays start to get, these gray areas start to get a little more lenticular. They get to sort of be flat discs, you might say. These gray things are more flat discs laying out here, but still there's quite a bit of connection among the whiter areas, which are the sandy areas. And even in these areas where actually this upper part geologically is considered the equivalent of the 180-foot aquifer, and this lower part geologically is considered the equivalent of the 400-foot aquifer, and you see there are big gaps. There isn't a continuous aquitard across them. And so therefore, we are considering the forebay aquifer subbasin as a single aquifer there. At least the 180-400. Now there is some question, I'm probably going to change this because we changed this just yesterday in a conversation. The 180 and the 400 we're calling the basin fill aquifer. Some groups have called the Arroyo Seco cone a separate aquifer. We're not sure we're going to do it. We were discussing this with the Arroyo Seco GSA's technical consultant yesterday, and there's a good chance we are probably going to say the Arroyo Seco cone is stratigraphically different. It is hydrologically different, but it's not a separate aquifer. It is part of the same aquifer system. It just looks significantly different as far as the hydraulic conductivity of it. So this might change quickly, that we might now say the 180 and 400 and the Arroyo Seco cone constitute one aquifer, although it changes significantly place to place. There is a question whether the deep aquifer, which would be down here in the very lower left side of this picture, whether that is the extent of the deep aquifer or not. We don't know. There isn't a lot of information about it. The bottom of the basin drops steeply and dips steeply at the end of the forebay subbasin. And so there is some suggestion that the geologic deep aquifer comes into the forebay just a little bit and then stops. That's something that still has to be investigated, and we will not know that answer by the time these GSPs are written. It will, for a while, it will be an unknown there. The hydrograph, this is one hydrograph. There are a number of different signatures of hydrographs in the forebay. If you are next to the river, and in some places near the Arroyo Seco, you are going to see very flat hydrographs because they get a lot of recharge from the river, similar to the upper valley. However, in some parts of the forebay, you see more variation than you do in the upper valley. So that's why I included this hydrograph, because it's at least somewhat new and different than what I showed you before. And so we see actually more fluctuation based on year, climate, things like that. But we don't see a huge drop in water levels. You could make a good case that starting at about 2000, which is here, we've seen a slow decline in some of the hydrographs here. And this was a discussion that's ongoing with the Arroyo Seco GSA's technical consultant about this slow decline. How much is an actual decline in water due to water use or just climate? That's something that we're still discussing. So slightly different, but somewhat similar to the upper valley. Then when we get to the 180, 400-foot aquifer subbasin, there, as everybody knows, there's three aquifers, the 180, 400, and deep. And you see that these gray aquitards are laterally extensive. They are thick and laterally extensive. The aquifers sit between them. This is the 180-foot aquifer. This is the 400-foot aquifer. Because of these thick aquitards, the recharge from the Salinas River is limited. I'm not saying it is non-existent. I'm just saying it's limited compared to the forebay and the upper valley. You do get recharge though, as I mentioned earlier, these 180 and 400 foot aquifers are the same geologically. They're geologically the same aquifers that go into the forebay. So we do get some inflow from the forebay, and I'm going to discuss that in a few minutes here. Groundwater elevations, you'll notice, don't drop off very much, even though these are confined aquifers. And the reason they don't drop off the way you would see, say, in the Seaside Basin, which is also confined, also near the ocean, is because the groundwater elevations are effectively being maintained by seawater intrusion. So it's not a good thing, but that's why we don't see a groundwater elevation drop off. In the Seaside Basin, you do see groundwater elevations dropping precipitously, but they don't have seawater intrusion. So it's sort of a name your poison problem there. So those are the three that are in line. We go from very unconfined to slightly more confined to very confined, although they are all connected in a line there. And this is the confinement. You can see it in the 180-400. These are two wells that are water levels in two wells that are next to each other. So in the 180-400, you see that one shallow well has very high water levels. A deeper well has much lower water levels. This is a vertical, what we call a vertical gradient. There is a big water level difference between the shallow and the deep because water is not flowing from the shallow to the deep area very easily to fill in these low water levels. Low water levels should draw water towards it, but the aquitard between these two wells is preventing water from flowing down from the shallow well to the deep well. So you see this gradient. Different than the forebay. Here in the forebay, you see two wells. This is actually two wells, a blue one and a yellow one, but the groundwater elevations effectively plot on top of each other. Because if pumping happens at the deeper zone, water flows from the shallower into it very quickly. So basically the water levels in any shallow or deeper well are going to be very similar to each other. You don't see these vertical gradients. It means in the forebay, you don't nearly see the level of confinement. It means it's easier to recharge the forebay than it is the 180-400. That's the take-home message. Getting away from the Salinas River gets a little more complicated because we have varying geology. We have a lot more alluvial and fluvial geology. There is no direct recharge from the Salinas River. The Salinas River only goes through those three subbasins, so we don't get direct recharge. And although these subbasins are still hydraulically connected. Now the east side has some limited connection. I'll talk about that. When I talk about alluvial fans, this is a drawing of an alluvial fan, and it might not make sense to you all immediately, but when you think of it, think about driving through the arid Southwest and you see these big cone-shaped fans coming off the hills and the mesas. That's what an alluvial fan is. And alluvial fans are, it's important to talk about them because they are discontinuous sands and gravels. Remember I said those fluvial river deposits have long sands that are all connected, and long gravels and long clays that are all connected. Not true in alluvial deposits. They have a tendency to be disconnected. The Arroyo Seco is a little different, but this is in general. So you don't get laterally extensive aquifers. And that's what the east side is like. It doesn't have laterally extensive aquifers. It's all these interconnected alluvial fans. The east side is also not well connected to surrounding basins. It's not disconnected, but water, because the aquifers aren't connected to each other, you don't get water flowing easily down a single aquifer. Water in one subbasin has to kind of find its way to the aquifers in the east side. So they aren't well connected. You get limited recharge from surrounding aquifers. Most of your recharge comes from precipitation and local runoff. This is the cross section again, like I'm always trying to do, showing this is our working cross section right now of the east side aquifer subbasin. You'll notice that there aren't any long connected clear areas, the aquifers. They are just pockets basically, except for this area. And we're looking into this. Is this a real indication of a very sandy part of the east side aquifer or not? That's not the point of this discussion, but I just want to point out we are looking into this. But in general, you don't see long aquifers. You see hit and miss aquifers, and the water levels. Now this is taken at the north end of the east side aquifer. It has been declining over time. I say the north end because one of the issues about these types of aquifers, which are not well connected, is this type of signature groundwater level might not translate a long distance. It might be the drop in the water level in one of its pockets, but a pocket some way away, a pocket of sand some way away, since it's so disconnected, might not see this same drop in water level. So one of the issues we deal with when on the east side, when we're talking about projects, is some of the solutions, problems and solutions might be localized as opposed to more sub-basin wide there. And it has to do with this type of geology. The Monterey subbasin is geologically similar to the 18400. Although the 180-foot aquifer appears to be absent in the southern portion. As you see, this is some of the geology actually kicks up, and so we actually end up losing the 180-foot aquifer when you get to the southern portion of the Monterey subbasin, it looks like to us right now. It is near the Salinas River, so we might be getting indirect recharge from the Salinas River, but again, like in the 18400, it's limited by the aquitards. You do get recharge from neighboring basins and precipitation. There is relatively limited data in this subbasin, except for Marina Coast Water District and some Fort Ord remediation and Fort Ord work. So we don't have a lot of data. The hydrographs that we're showing here are interesting because they do show the vertical gradient here. The yellow hydrograph is a shallow well in the dune sands near the coast, and the gray and blue hydrographs are the deeper wells in the 180 and 400-foot aquifer. You don't see a long decline over time. You just see a significant vertical gradient between what is the water in the dune sands and the water levels in the deeper aquifers there. So Monterey subbasin, like I say, very similar to the 18400. There's a few geologic differences, but also a little farther from the Salinas River. It's going to make it a little more difficult to get recharge water to the Monterey subbasin. Finally, the Langley subbasin, it is also somewhat distinct. It is very thin. Its main identifying feature is that the aquifers are very thin. Many of the wells draw water from the underlying fractured bedrock, which I'm showing here as these blue lines are fractures. So think of it as fractured granite. If you think of what the Sierras look like, that's fractured granite. Think of that. And there are fractures in here. And so a lot of the wells poke into that. It means there is limited water supply in the Langley subbasin. It's a very thin aquifer, and a lot of people are drawing from where there's limited supply. Because of this, we see some areas that show long declines in groundwater levels. It's not sustainable at that rate. But similar to the east side, these are aquifers that may have localized conditions and localized problems more than they have regional problems. So again, when we're talking about what projects work in the Langley subbasin and how does that subbasin work, that subbasin works probably on a very localized scale compared to, say, the Forebay or the Upper Valley or the 18400, which work on very regional scales there. As I said, all of these subbasins are connected. What does the flow between the subareas look like? This was the estimates from the 2015 State of the Basin report, Brown and Caldwell's report. It is based on water sub-area, not the subbasins we're working with, because that report is written for water resource agencies' sub-areas. So it's not a one-to-one correlation of each of the subbasins, but it'll give you an idea of what happens. The subsurface inflow is in this column, and you can see what it is for the various basins. The pressure gets about 17,000 acre feet. The Forebay gets about 31,000 acre feet by their estimates there. The inflow accounts for between 4% and 29% of the water supplies in each of these sub-areas. 4% is not a very big one, that's the Upper Valley. 29% is the east side, according to their calculations. It is significant. So this amount of interconnection can be an important factor there. But it's going to change place to place. I want to bring that up because I keep bringing up over and over, solutions to our problems are regional solutions. And so in some places, regional solutions, if you try and implement a solution in one of your subbasins, it is going to impact the other subbasins. Of course, this subsurface flow is only a portion of the water budget, and I'm not going to go into water budgets because When I think of water budgets, if you wonder what a hydrologist thinks about, this is an example water budget. This is actually the water budget that I'm putting together in my mind for each of the subbasins. These are all the parts of it that I've put together in my mind. This little arrow down at the bottom is what we were just talking about, flow in and out of adjacent basins. All of these other things go into the water budget. This is not a talk on water budgets, but this is the way we have to analyze things to figure out how are we going to get to sustainability. So that is how the groundwater system works. I'm only going to do a couple more slides right now to make sure everybody's up to speed on a couple more things. Because actually, let me take a stop right here because I'm going to change subjects a little. Emily, do we have any questions?
Yes. I see one from Steve McIntyre. Go
Thank
ahead,
you.
Steve.
Thank you, Emily. Derek, when you refer to that sandy area that you're going to be investigating in the east side, do you know approximately where that is on the map?
Yeah, and where is it? It is, Steve, I'm going to answer your question and say, yes, I do. And I've forgotten exactly where it is because I did look it up. And I don't know, Jason, did we talk? Jason might know because I think we might have talked about this. Jason Smith, did we talk about where this is with you at one point?
You know what? I've been in the middle of sending smoke taint emails.
Oh, okay.
So I'm out of exactly where we're looking at. But we
Yeah.
Yeah.
This is along one of the major creeks that comes out of the Gavilan Range, I know, and I forget which creek it is, but it is one of the major creeks. It's right along one of those major creeks, Steve, and I forget where it is.
Thank you.
Derek, can you hear me?
Yeah, Tom, I can hear you.
Was it Chular Canyon? I remember you talking about that at one of the past meetings.
It might have been. It might have been. I forget. I'll have to look. If I talked about it at one of the past meetings, it probably is then because it would have been the reason I brought it up. So it might have been that one. Now, but Steve, I'll look into that. We have talked to some people on the east side and said if we have more data around here, we would like to know about it because if it truly is this thick sandy zone, it means it's going to be a zone that's very good for easy percolation of surface water, and that's what we're looking at. So that's
what I'm thinking. Yeah, thank you.
Okay, Robin Lee, go ahead.
Yeah, I know there's some percolation had been found along San Juan Gray Road. This would be on the north end of the east side subbasin near the Langley. I think they're sharing a little bit of a percolation area from your past talks about each subbasin, and that comes down out of the Gavilan Creek area. But it's a ways from it though. It's on the, well, it's not too far, but that's been identified as possible percolation places in the past. So I don't know if that's part of your sandy area or not. But
Robin, that's not the sandy area I'm showing there, but if you would attend the Langley, I don't know if you're planning on attending the Langley committee meeting and bring that up again, because we're going to be talking about potential projects and potential recharge areas. I would appreciate you bringing that up again at the Langley committee meeting if you are planning on attending.
okay.
So September 2nd at 10 o'clock.
Thank you, Emily.
Okay, let's see. An attendee is raising hand 0312. I'm asking you to unmute. There you go. Go
Besides
ahead.
that, somebody's speaking in here, so I couldn't hear what you said.
Go ahead. Do you have a question?
Yes, I wanted to ask about the ancient aquifer and the 140, 800 foot aquifer. There's a 900 ancient aquifer, and I just wondered if you have any knowledge of the recharge situation with that particular aquifer.
Yeah, good question. And I'm going to duck this one a little and say, no, I don't. And this was this came up in a question, earlier question about how much I'm going to talk about the deep aquifer, and really not much except for it is, next in line below the 180 and 400, and it acts as a confined aquifer in the same way they do. The question of where that deep aquifer gets recharged is a point of contention that has been around for some time. I do not want to opine on it now because it is an important question and I don't have enough data. In general, if you had a basin that was sealed on all sides and you had a deep aquifer, you would say it gets very little recharge because all the recharge has to come from the ground surface. It has to percolate through a lot of clays before it would get to a deep aquifer like the 900, 1500 foot deep aquifers. That said, remember I pointed out the question of, does that deep aquifer go all the way into the forebay, subbasin, where there are fewer confining beds? And is there an opportunity for that deep aquifer to get recharged all the way up in the forebay? I don't know the answer to that. That is a point that is going to be addressed in an upcoming deep aquifer investigation. But the reason that investigation has to happen is because we don't know the answer to your question. It's a great question. I wish we did, but I'm sorry I can't answer it.
Well, thank you, Derek, for trying. You did give really great information. We have a lot of work to do.
If that's all I have to say, I can say that all day long. Yeah, we have a lot of work to do. Yeah, okay.
Thank you.
Thank you, Margaret. Okay, I don't see any additional hands.
The only things I want to touch on again at the end here are to talk about, when we talk about how things operate, there are some specific challenges, and particularly seawater intrusion. The major challenges in the Salinas Valley, as people know, are seawater intrusion, groundwater depletion, and groundwater depletion is partly a result of unequal access to recharge there. And I'm not saying that it is unequal in some sort of nefarious way. Geography does count. If you are at the upper end of the river, you get first, the river gets to you first, you get the most recharge there. But there is unequal access. And so part of our project's issue is going to be, how do we make more equal access to recharge water? Challenge, of course, is maintaining ecological benefits while we still do all these, and groundwater quality degradation is going to be a challenge. The only one I want to talk about a little is seawater intrusion, just to make sure everybody understands how seawater intrusion works, because it is important to know that if we need to know, if we're going to figure out how to solve the problem. And many of you will know this already, but I want to make sure everybody understands this. So seawater intrusion occurs because the aquifers, particularly the 180 foot and the 400, and probably the deep also, although we don't have much information about it yet, these aquifers are in some way connected to the ocean. What we're showing here is the aquifers just go to the edge of something like, let's say, Monterey Canyon or something, not here, but I know in some places it's Monterey Canyon, but and they probably do. But they probably, actually the 180 probably pokes out well before then. Let's just say they go to the edge of the ocean there. And so as we pump water out of the 180 or the 400 or the deep, some water is coming in to replace that water from the upland. Some water is coming in from the ocean to replace that water. And so that's where we get seawater intrusion. It just starts coming in. We want to be able to push it back out. What makes seawater intrusion particularly nefarious is that seawater is heavier than fresh water. And this is what you have to understand and what makes it difficult and what I want to make sure everybody knows. So for the same amount of seawater, which is in green, if we were to weigh it against the same amount of fresh water in blue, the seawater would weigh more there. And it's because of the salt that's in it. If we want to make those two things weigh the same, we would need more fresh water. We would have to add fresh water. And then we could get them to weigh the same. And this is the picture you ought to be looking at right here then. Now these two things weigh the same, which means they are going to push against each other at the same with the same amount of pressure. They weigh the same, they can push against each other with the same amount of pressure. Since the green is seawater, we can think of that dashed line as sea level. That's the level that seawater is at, right? Is sea level. You'll notice to push back against seawater, like I said, we needed more fresh water. Our water level, our freshwater level has to be well above sea level just to equate to the ocean. This isn't even to push the seawater back. This is the point at which we are just holding things steady, is to have our groundwater levels well above sea levels. Remember, sea level is the dashed line. And this comes from the fact that they have different weights. And if we want to start pushing seawater back, we have to add even more fresh water. Then we have to have even higher groundwater levels. And this is an important thing when we talk about how the basin operates and how to solve the seawater intrusion problem. It is not enough to raise groundwater levels to sea level. It's not even enough to raise groundwater levels a little above sea level, because a little above sea level just keeps things maybe at a standstill. It is well above sea level. What the phrase well above means is up for discussion, but well above sea level that you need to get to before you start driving seawater out there. And so it's important people understand that this is the mechanism for how this northern part of the basin operates if we are going to solve the seawater intrusion problem. So as a recap, the big picture items, all the water in the valley ultimately comes from rainfall. And our job is to organize the rainfall and to make sure that we can move it around in such a way that we provide reliability to decrease the seasonal, interannual, and spatial differences in water reliability, while at the same time acknowledging the environmental and water quality aspects that we have to acknowledge there. Current projects, there are 2 reservoirs in the CSIP. Those are the projects that are out there. And those are the projects that are defining how we operate the valley today. The projects that we're going to be coming up with the GSP are going to work with those, and they're going to work with those to define how we operate the valley in the future there. Some of the subbasins along the Salinas River have better access to recharge than those away from the river. Some of the subbasins are geologically unique, but they are all interconnected. So in doing a project in one subbasin is going to have an effect on any other subbasin, largely because the river runs through the entire valley. And that's why we have to fix all of the subbasins at the same time. Those are the real take-home messages. And like I said, based on that, I hope you've got an idea of how the basin works. So when we start talking about projects starting next week, you will have a vision in your mind of how the project is going to change how we operate the basin. And hopefully you will have in your mind a project you would like to see implemented so we can start modifying how we operate the basin. That's where we're going, and I'll take any more questions now.
Okay, let's see. Take a question from phone caller 0312.
That's me. The program operator is talking to me about my microphone. I do have a question for Derek. I was wondering if you could give a clarification on what constitutes the difference in the weight between the seawater and the fresh water. I know there's a difference in the total dissolved solids, seawater being mostly sodium chloride and sodium calcium is primarily fresh water. So I just was wondering what constitutes the difference in the weight that you mentioned.
It's because there's so much more salt in the seawater. Even though it's dissolved, it still adds weight. So the fresh water doesn't have that much salt in it, and it just, because of that, the weight of the salt is what makes the difference there. It's not whether it's sodium or calcium. It's just the total amount of salt that's actually been dissolved in the water. So even though you don't see it, it actually is significant.
Oh, thank you.
Okay, and now James Tynan.
Hello, it's Eric. I go by Eric, but I guess this is James.
It says,
Oh,
yeah, it says James on your little square, Eric, but I knew who you were.
I was like, oh, it must be a relative. Okay. Hi, Eric.
Did you know that we're losing well 3 right now? It's in the 400. It's right. It kind of justifies what the water resources contour is showing. So if I get a chance, I'll send you our graph on our wells that we had back to 2015. It shows all 4, including the deep well. So I think you might find it interesting.
I have not heard that. I'm sorry to hear that too, Eric. A good example of why we've got to get this done. I'm sorry to hear that, but yeah, I would appreciate the data if you've got it.
You'll get it. You'll get it today.
Thank you.
Okay, does anybody else have any questions? I don't see any additional hands.
Okay.
I'm gonna pull up my agenda here and make sure I keep on track. But thank you, Derek. That was a ton of information, and I'm always very grateful about our new Zoom capabilities, so that we can watch it again and get all the information that you just presented. So thank you, and both the recording and the presentation will be available on our website as soon as possible. So please check that out. And so moving on to staff reports. I don't have any staff reports unless Donna, you would like to have anything to add? I don't think so.
I do not. I
Okay.
do not. No, thank you.
And if any committee members would like to report on anything, you're welcome to do so at this time. Making sure I'm keeping track of the participants here. Let me see if okay, I don't see any raised hands. Okay, and future agenda items, just want, oh, I'm sorry, I don't have my video on. I will see. Hello, everybody. For our next workshop, we have it scheduled for September 30th from 2 to 4. And that will be on interconnected surface waters and groundwater dependent ecosystems. So please save that date, again, September 30th from 2 to 4. And with that, I will call this meeting.
Would you give a good pitch for the sub-basin committee meetings also? If you are a sub-basin committee member, the upcoming meetings are becoming very important for input from the sub-basin committee members.
Yes. Yes. So we look forward to your attendance. And again, they're open to members of the public or other sub-basin committee members from other sub-basins. You can participate as a member of the public. But yes, the next few meetings will be very important. The Langley is on September 2nd from 10 to 2. The Forebay is also on September 2nd from 1 to 3. And the Monterey sub-basin meeting is on Friday, September 4th from 10 to 12. So,
Emily, before you adjourn, just wanted to flag any other public comments before.
Oh, thank you. Mm-hmm. Let me just keep losing my little participant thing. I don't see any additional hands raised.
Okay.
Oh, wait, sorry, one attendee. Eric Tynan, is your hands raised from earlier? Or
Yeah.
Go ahead.
Yeah, I just wanted to mention today the Coastal Commission staff released a report that's recommending denial of the slant wells for the, I don't know if you're aware of that, but that's kind of a big deal for us. So,
Yeah. Wow.
If anybody wants to report, let me know and I can send it to you.
Okay, thank you. Okay, any other comments? see. I see a hand raised. Where are you? There we go. Matt Simus.
Where on the workshop, on the website, is the workshop materials? I don't see that anywhere.
Yeah, so you go to, I'm going to the website right now. I can walk you through it. You go to the GSP tab on the website.
Okay.
Then you go to subbasins.
Okay.
And then in the bottom of there, you'll see that's where you'll get to the links with all the information for each of the subbasins and the draft chapters as they're released. And on the bottom is the workshops.
Perfect. Thank you.
My pleasure. Okay, well, thanks again to everybody, for your time and participation today. And thanks as always to Derek for your wealth of information. And so with that, I will call this meeting adjourned.
Thank you.
Thanks a
Thank
lot,
you,
Derek.
everybody.
There.
Thank you.